Howdy folks, welcome to our final video from Chapter 1, our Introduction to Physics. Now this video is going to be a little more on the math side, because of course one of the biggest tools of physics is math. You could not do physics without math, and in fact, physicists throughout history have literally invented new types of math to be able to do their physics. The most famous example probably being Isaac Newton inventing calculus to be able to do more physics. And trust me, folks, this is algebra based, but the beauty of calculus based physics cannot be described. It's amazing, and I would love if everyone in the world could learn calculus and calculus based physics. It just makes life and the universe just beautiful to behold on so many levels. But I digress. Let's focus more on our algebra-based physics and the tools that you guys will need to get through this class. So specifically, I want to focus heavily on exponents and scientific notation, and I'll talk a little bit about significant digits as well before it's all over. So exponents, you may be familiar with them. You may not. Regardless, you're going to need to brush up on them for this class. Exponents are used to show repeated multiplication. So if you have something like x squared, it means two x's, x times x. X cubed, or x to the third power, x times x times x. Repeated multiplication. Negative exponents show repeated division. So if you have x to the minus 2, it means divide by x twice. Or x to the minus 3 means divide by x 3 times. Or 1 over x times x, 1 over x times x times x. That's the basic way that we represent numbers with exponents. Now in these examples, you would call x the base, and the number is the exponent. And now we're going to use this jargon throughout the rest of this video, so make sure you have this clear. X, in this case, would be the base. The number is the exponent. And there are special rules for multiplying and dividing exponents, specifically with the same base. That is very important. This doesn't work otherwise. So if you have something like x squared times x cubed, well, that's x times x for x squared times x times x times x for the x cubed. But if we take a step back and look at this, well, that's really just x times x times x times x times x. 5 x's multiplied together, well, we can write that as x to the 5th. 5 times that we're doing that same multiplication. So really, x squared times x cubed equals x to the 5th. And if you look at that, if we almost squint a little, or if I shift this paper up and you can only see those exponents, that sure looks a whole lot like 2 plus 3 equals 5. And in fact, it is. That is the rule. When multiplying exponents with the same base, remember that part is important, has to have the same base, you add the exponents. And so we don't actually have to write out all these x's and count them. We can simply look at, oh, there's going to be 2 of them and 3 more of them. Well, that ends up with 5 of them, x to the 5th. And it works very similarly for division. If we have x to the 5th divided by x to the 3rd, well, we can write it all out. X times x times x times x times x divided by x times x times x. And if you have the same thing on the top and bottom of a fraction, you can cancel it. So we can cancel 3 of those x's. At that point, we've run out of things on the bottom. But what we're left with are 2 x's, or x squared. And so we can see that x to the 5th over x to the 3rd is x to the 2nd power. And just like 2 plus 3 equaled 5, we can see a relation here. 5 minus those 3 that were on the bottom left us with 2 up top. 5 minus 3 equals 2. When dividing exponents with the same base, you can subtract the exponent on the bottom from the exponent on the top. And there's one more rule. I don't think we'll come across it in this class, but I would feel remiss if I did not include it here. And that's exponents raised to exponents. X cubed to the power of 2, x cubed squared. Well, we know that squared means the same thing twice, x cubed times x cubed. And each of those x cubes are x times x times x. Well, we count them all up. Sure enough, 6 x's, x to the 6th. X cubed to the 2nd power equals x to the 6th. Well, this looks like multiplication. 3 times 2 equals 6. If you have exponents raised to exponents, you multiply those exponents together. And as I said, I'm not certain we'll use that rule, but it goes hand in hand with the others. So I felt as if I should go ahead and include it here for completeness. Alrighty, so the next topic is scientific notation, and here's where we're going to start seeing these exponents pop up more and more. Scientific notation is a way to make our lives easier so that teachers and physicists don't end up with carpal tunnel. So here I've written a very big number. Let me see, this would be a million, billion. That is a trillion. I wrote 1 trillion. And sure enough, it is a big number. I'd agree with that. I think you'd agree with that. However, I don't like writing out 12 zeros. To make it easier to write, we use scientific notation. To use scientific notation, you move the decimal until only one number remains to the left of that decimal. So I take this 1 trillion and I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal places over. And that tells me how many powers of 10 I moved. So this would be 1, you leave the number off to the left, times 10 to the 12. How many tens? How many decimal places? 1 times 10 to the 12. And in this case, since 1 times something is always that something, we could just call this 10 to the 12. But let's look at a slightly different case where we need to keep that number. What if it's 1.5 trillion? 1 trillion 500 billion. Very similar. We start off with our decimal place here. We move it over and over and over and over and over. We can count it 12 times until we get to only one number left over there. That gives us our 10 to the 12, and what I'm left with is 1.5. 1.5 times 10 to the 12. So much easier to write than all those zeros. So that's one advantage of scientific notation. It just makes things a little more easy to write, a little more succinct, nice and tight and compact. One more example, just to drill this in and have it switch up a tiny bit. I now have 21 trillion 500 billion. Well, now the number's even bigger. I actually have another place I have to move over. So instead of going 12 decimal places over, I actually have to go one more 13 times until I only have one number left over, this 2 out front. And so I would have 2 decimal place 15, 2.15 times 10 to the 13 powers that I moved over. So you know that because you counted over 13, that is your exponent here. Just wanted to make it clear that it's just not always 12. It is however many you count over. So that is the basic idea of representing a number in scientific notation. Now let's combine this with the exponent rules we just talked about. Exponent rules make it really easy to do math with numbers in scientific notation because the base is always 10. 10 to the something, 10 to the something, 10 to the something. Just like on the previous page, the base was always x. When using scientific notation, your base will always be 10. And remember, the base has to be the same for those exponent rules to work. By using scientific notation, you guarantee this. You're always going to have base 10. That means they combine easily. And the same goes for metric prefixes. Remember we talked about those just a couple videos back. Metric prefixes, kilo means times 10 to the 3rd. This means these powers of 10 show up a lot in physics, and it means it's very easy to combine them. So if I have 2 really big numbers, say I had to multiply these 2 together, I could multiply 1.5 times 2.15. I'd get a number, about 3 something. And then these just combine quickly. 10 to the 12 times 10 to the 13, I know immediately is 10 to the 25, because I just have to add 12 plus 13. Otherwise those would be huge numbers to deal with. Tons of zeros, 25 zeros to write out. But instead I can write it nice and quick, and I can do the math in my head because I'm simplifying these huge numbers into quick little addition problems. Now, we're not going to use huge numbers all the time in this class, but they will pop up from time to time, and I would like you guys to be prepared for that whenever they do happen to make an appearance. All right, now lastly, I want to talk a little bit about significant digits. Now, you might have heard about significant digits in a previous science class, maybe chemistry or physics in high school. And a lot of people don't understand them at first, but significant digits really aren't that bad. I like to really make it clear why we use them, rather than just saying these things exist and these are the rules. I like to start with where they come from. Significant digits illustrate how much information you know. It's a reflection of the precision of your measuring instrument. If I'm going to pull out a ruler, well, this ruler has, let me turn it around for the centimeters. It has centimeters, and then it also has millimeter marks. So I know I can definitely measure to the millimeters, and we'll actually take it a step further than that. I've got a little fake centimeter ruler drawn right here. If I were to say, where does that arrow measure right there, and explicitly how many significant digits, well, first we can see it, well, it's beyond the 1. That means we have 1 centimeter. It's beyond that second notch there, which means it's beyond 1.2. So we definitely know that it is at least 1.2 centimeters. And then, in fact, we can actually then take a guess for one more digit, because I know it's not exactly 1.2. It's not right on that line. It's not at 1.3 yet, and you can make an approximation. If you don't feel comfortable, picking a number, you could always just say point. You can always take halfway through, or a 5 for that digit, and I just chose an arbitrary number really for this. But you know that it is 1. It's also past 0.2, and you know a little more information from how far between that 0.2 and 0.3 it is. And so I've estimated this to be 1.22 centimeters. You do the precision of the instrument, what's actually marked on it, and 1 extra, plus 1 estimated digit. And I really know that information. I couldn't guarantee on my life that that's 0.2, but that is a good approximation. I am confident, at least, in reporting that number. That's where significant digits come from. They come from how much you know. Now, students are very prone to, plugging some numbers into a calculator and giving about 10 digits after that decimal place. Now, do you really know that measurement to that accuracy? No, I couldn't tell you what the millionths of a centimeter are. That's way past what I can see or what that instrument can do. But this definitely goes to the tenths place, and I can make a good estimation or approximation of that hundreds place. So, now that you know where significant digits come from, the 2 rules that you need to know are how to combine them. Now, when adding numbers with significant digits, you keep the least number of decimal places. Now, if I were to try to add, something I only knew to the whole number, if I were to add something that was 1 centimeter to this, I don't really know what I'm adding here. I'll illustrate this more and stress this more in lab. But just in case you don't have me for lab, that would be like saying we're adding 1.22 plus 1. Well, if I don't actually know any information, this is like question mark, question mark. Can I add 2 to question mark? No, this is still unknown. This is still unknown. If I only have 1 significant digit there, that's all I can really confidently report back, that this is about 2. I don't know what this next digit is, or definitely not the digit after that. That is why when adding, you keep the least number of decimal places. That might even be 0, or it might even be the tens place or the hundredths place. You keep the least number of digits that you know. When multiplying, you keep the least total number of significant digits. And it's a little more complicated in terms of illustrating that, but that's a rule that's very easy to follow. You count your significant digits, 1, 2, 3. If I multiplied this by that number like 1, well, it's only got 1 significant digit. You then only keep 1 significant digit. You keep the least number of significant digits. So this will be very important in lab. It's a little weirder when working homework problems. We give you sort of artificial significant digits, But in lab, it's very practical. You only know so much information, so don't try to represent to me that you know more than you actually do. When you try to write out decimal place after decimal place, I will challenge you. Do you really know that that thing, has such and such millionth of a centimeter on it? No, you don't really know that. So that is why we use significant digits. They represent an amount of information we know, how precise our measuring instruments are. And this is a big deal in the real world science that goes on out there. Proving how you know what you know is important, and understanding those limits of your knowledge is just as important as your results that you're actually getting. All right, so if you guys have any questions over any of this, feel free to reach out to me. If you're watching this from from another section, if you can track me down, I'll still probably answer questions for you. But feel free to ask questions. Never hesitate to reach out to your professor, whomever that may be. Particularly if it's me, I love answering questions, answering emails. Don't hesitate to reach out. But that actually concludes the first chapter. We are done with our introduction to physics. Next week we will start with some real concepts and equations as we get into motion. And I look forward to it. It's going to be a lot of fun. I have a passion for this, and I hope to share that with you guys as well. So see you next week. Take care. Ta-ta for now.